Greetings all of you, respected Sir Dr. C.P. Khatiwada. I am Tashi Chitin Lepcha, bearing roll number 159, present you the project on Einstein Coefficient A and B. In 1917, 9 years before the development of relevant quantum theory, Albert Einstein, who was a theoretical physicist, postulated on thermodynamic ground that probability of spontaneous emission A was related to probability of stimulated emission B by the relationship A by B 8 pi h nu raised to the power 3 divided by c cube. From the development of the theory behind blackbody radiation, it was known that the equilibrium radiation energy density per unit volume per unit frequency was equal to. Einstein argued that equilibrium would be possible and the laws of thermodynamics will be obeyed only if the ratio of the A and B coefficient have the same value shown above. The ratio was calculated from quantum mechanics in the mid-1920s, and in recognition of Einstein insight, the coefficient have continued to be called the Einstein Coefficient A and B. It was the brief introduction about topic. Now let's move on for the derivation and calculation part, where we show the relationship between Einstein Coefficient A and B. But before starting, we should have some knowledge about some terms which are in absorption of light. When the atom in ground state absorbs light, it goes to the excited state. Similarly, spontaneous emission is a phenomena where the atoms come down by itself without any external force and emit a photon. Stimulated emission is a phenomena where the atoms on excited state is struck by external energy. It comes down and emit a photon. Two physical quantities are in thermal equilibrium. There is no net flow of thermal energy between them when they are connected by a path preamble to heat. Thermal equilibrium obeys the zeroth law of thermodynamics. From Boltzman Distribution Law we get. Similarly, from Planck's distribution law we get. Now let's proceed to the calculation part. So now, doing the calculation or derivation part, we know rate equation or equation of transition for absorption is dN1 by dt. It is the mathematical form of rate equation for absorption. ABS means absorption is equals to N1 B1 to U omega, where N1 is equal to number of population in ground state. B12 means the atom traveling from ground state to excited state. So U omega means external energy, as before in the video the absorption means in the medium the atom in the ground state absorbs the energy from light. It absorbs the energy from light and it travels to the excited state. So this was the phenomena of absorption. So This is why the external energy is written in the or required in the mathematical expression. Similarly, rate equation for spontaneous emission. As we know, spontaneous emission, let excited state denoted by Ex and ground state by Gr. Now, as we know, in spontaneous emission, the excited atom itself falls down or comes down and emit one photon. So the external energy is not required or not used. So the mathematical equation or rate equation for spontaneous emission will be dN2 by dt. N2 means the atom is in the excited state, means number of population in excited state. Let it denote by spontaneous, so is equal to N2 means number of population in excited state. So external energy is not required, not performed, or external energy is not used. So the constant A means the constant A is 2, 1. Let it be equation number 2. Similarly, rate equation for stimulated emission. If we recall, stimulated emission means the atom in the excited state is struck by the energy, so it will come down to the, it approaches to the ground state and it emit the photon. So representing it in mathematical form, we can write dN2 means N2 N1. The population is of excited state means N2, dt stimulated is equals to N2. Number of population B constant 2 to 1. External energy required, so U omega. Let it be equation number 3. So now from thermal equilibrium condition, thermal equilibrium condition means if you take the jar of cold water, means cold water, it is chilled in the refrigerator or something else. Let's take the jar with the normal room temperature and let's take the jar of hot water. So after certain, and let it be in the room, and after certain time the temperature of 3 jar will be same. So for thermal equilibrium condition, number of upward transition is equals to number of downward transition. So dN1 by dt from equation 1 ABS is equals to dN2 by dt spontaneous plus dN2 by dt stimulation. We take this one in this side because in spontaneous emission and stimulated emission, the transition is occurring from N2 to N1. So as from thermal equilibrium condition, number of upward transition, number of downward transition is equal. So in absorption condition, the atom was traveling upward So further solving, n1 b12 u omega, substituting the value of equation 1, dn2 dt means n2 a21 plus n2 b21 u omega u omega. Now let take u omega as common. U omega bracket open n1 b12 minus n2 b21 bracket close is equals to n2 a21. So now u omega is equals to by rearranging n2 a21, we are taking this function to this side, n1 b12 minus n2 b21. So u omega is equal to a21 by n1 n2 b12 minus b21. So u omega is equals to a21 by n1 n2 b12 minus b21. Let it be equation number 4. Now we know from Boltzman Distribution Law, we get n is equals to n naught e minus e by kt. Hence n1 is equals to n0 e e1 kt, and applying in n2 n naught e e2 kt. So putting the value of n1 and n2 in equation 4, we get u omega is equals to a21 divided by e2 minus e1 by kt b12 minus b21 by taking commons. U omega is equals to a21 by b12 e h nu by kt minus b21 by b12. Let it be equation number 5. So now from Planck's radiation law, u omega is equals to 8 by h nu omega a cube by c cube bracket open 1 by e h nu by kt minus 1 bracket close. Let it be equation number 6. Now comparing equation number 5 and equation number 6, we get a21 by b12 is equal to 8 by h nu cube by c cube. Let it be equation number 7. And b21 by b12 is equals to 1. b21 is equals to b12. Let it be equation number 8. These equations 7 and 8 are representing Einstein coefficient. So thank you. Hope you like the video. Please hit the like button, share and comment.